Hello friends, here in this video we will see the design procedure for knuckle joint. Now for that purpose, here I have a diagram of a knuckle joint. This joint is used in case of tensile applications, that is where we are applying pull type of load. As it is clearly seen from the diagram, knuckle joint consists of single eye end, which I have written here. It is hollow. Then we have double eye end. Now the other name of double eye end, it is also called as fork end, since it is like a fork. Now this single eye end would be inserted into the double eye end, and then we are having this knuckle pin which will be attached, and here also there is a pin. So this system becomes a locked system. The assembly gets completed. Next, on single eye end, here we are applying load P, which is towards right. On double eye end, here we are applying a load which is towards left. So because of these two action of opposite forces in two directions, the knuckle joint, it gets pulled. And this knuckle joint would be designed only for static load, not for dynamic load. Now, the major dimensions which I can see here is the rod, which has the minimum diameter. It is denoted by small d. Small t is the thickness of this single eye end. T1 is the thickness of this double eye end or fork end. Next, here I will denote small d1 as the diameter of single eye end, and fork end, the diameter would be same. Knuckle pin diameter, I'll keep it equal to the diameter of this rod. So now let us analyze the failure one by one. Since we can see in this diagram, small d is the minimum diameter and failure will take place at minimum area. So first step number 1 will be design of this rod where the area is minimum. It means knuckle joint, there is a possibility in it to fail at this rod first. So step number 1 in design procedure of knuckle joint. In this design procedure of knuckle joint, our step number 1 is design of rod. And once the rod fails, it would be looking like this, that is circular in section, having its diameter as small d. Now this is the resisting area, and it is A is equal to pi by 4 d square, because when we are pulling this rod, the failure area which we will see, it will be in the form of a circle. D is the diameter of this rod. So here I have the resisting area. After this I can say that therefore, considering failure of rod under tension, now this knuckle joint is used only, I am mentioning only, it is used in case of tensile application, tensile loads, because if we apply compressive load to the knuckle joint, there are chances of this joint to slip, because it will provide angular motion also. So it is applicable only for tensile applications. Now considering failure of rod under tension, therefore I'll write down tensile strength of rod. It will be given by, now as I have explained, strength is nothing but load carrying capacity P, and that is equal to stress into area. Since here we are taking tensile failure under consideration. So it will be tensile stress into area. So therefore P is equal to, area is pi by 4 d square multiplied by sigma t. So here I'll call this as equation number 1, and therefore I can say that from equation 1, d, that is the diameter of this rod, can be calculated. Now this completes step number 1. In step number 2, I will be designing this single eye end. So in step number 2, it is design of single eye end. Now when we are considering single eye end, here I will draw the diagram of it in a 3D manner, that how it looks like. This diagram which I am drawing, it is for a single eye end. It will look something like this. And here we have a rod which is attached to it. This single eye end, it is hollow. It means the knuckle pin can be inserted here. So single eye end looks something like this. Now I'll say that let this outer diameter of the single eye end be denoted by D1, and this inner diameter is nothing but diameter of knuckle pin. Here I'll say that this is the diameter of knuckle pin denoted by small d. Now once I have designed in step number 1 the diameter of rod, after that I'll say that therefore let diameter of knuckle pin be equal to the diameter of rod. So therefore the diameter of knuckle pin, that will be equal to the diameter of rod, and diameter of rod is d. So here I have this hollow portion where the knuckle pin would be inserted, internal diameter of single eye end. Now I will see in how many cases this single eye end can fail. The first chance is that when I am applying load at the single eye end, this portion, it can split into half, means the single eye end would be splitting into half. Now we will see the failure of this single eye end. There are chances of this single eye end to split into two halves like this. From its center it would be splitting, and when I draw the failure diagram, it will look something like this. This is the single eye end after it has failed under tension, and another portion would be in front of it. So here the single eye end would be splitting into two parts like this. So this is a tensile failure, and here we are getting this as the resisting area. These portion, they are the resisting area. I'll draw this resisting area here. Now here I'll say that this is the diameter of knuckle pin which would be inserted, that is the internal diameter of single iron. This is the external diameter which is denoted by D1, and here is the thickness which is denoted by T. So this is the resisting area. So I'll say that since considering the first kind of failure, that is tensile failure for single eye end, the resisting area will be, since resisting area capital A, that will be equal to D1 minus D, that is area of these portion which I have sectioned. So it will be D1 minus D into T, the same resisting area which we have here. So therefore tensile strength of single eye end, strength as we are considering tensile, so it will be, strength is the load carrying capacity, that is stress, tensile stress into area, because tensile strength we are trying to get. So therefore P will be equal to, area is D1 minus D into T, we have calculated the resisting area, multiplied by tensile stress. So this is my second equation. Now I can say that from this equation we can get D1, which is the outer diameter for this single eye end. I'll say that therefore from equation number 2, either I can get D or I can get T, which is the thickness of single eye end. D or T can be calculated, because either I can fix any one dimension by using the relation which is called as empirical relation, and then I can find any one of the values. So this was regarding the tensile consideration. After this, again in step number 2, that is design of single eye end. Next I'll consider shearing failure. So considering shearing failure, now what is meant by shear is that when we are applying a load to this single eye end, there are chances of it to slide from here, that is this section, it will be sheared off. So it will look something like this when I draw that. So now this is the area, and here I'll say that this is the center of the knuckle joint, the center line of the knuckle pin. Now this much is the radius, which I'll say that this is small r, radius of knuckle pin, and that is nothing but d by 2. And this is the outer radius, which I'll call it as r1, that is equal to d1 by 2. And here I have this as the thickness of single eye end. So this is the resisting area. Now after getting this resisting area, since I'll get two pairs of area, one will be here, another will be behind, so I'll say that therefore resisting area capital A, it will be equal to here I have R1 minus this R into T, area of this rectangle, which is shearing. So R1 is D1 by 2 minus R is D by 2 multiplied by 2, since this is a case of double shear, and next I'll multiply it by T. Then I can simplify this. Area becomes, this 2 I can take common denominator and it will get cancelled out. So area is D1 minus D into T. This is the resisting area under shear. So after this I can say that therefore shearing strength of single eye end, shearing strength is load, since we are finding shearing, so that is shear stress into area, which is the resisting area. So therefore P is equal to, area is, we have found out, D1 minus D into T, and stress is tau. So this becomes my equation number 3. So I can say that from equation number 3, either we can check D1, we can calculate the value of D1 or T, or we can check shear stress. So we can say that equation number 3 is used for checking of shear stress tau or D1. Now this was the shearing failure of single eye end. Next we will see crushing failure. Crushing of single eye end. Now single eye end, how it will crush is that from the diagram, single eye end and knuckle pin both are made up of metal. So here we are seeing the crushing of single eye end. As it is seen from this diagram, single eye end is in with contact with the knuckle pin. Both are made up of metals. So when we are applying this tensile load, there are chances of metal to metal rubbing between single eye end and knuckle pin, and that results in crushing. Crushing is a phenomena in which the metal, they get converted into small fine powders, and if it is so, then the object is failing. So here I will draw the crushing failure diagram. The area which we would be getting, it is the projected area which will get crushed like this. Here T is the thickness of single eye end, and this is the diameter of knuckle pin, denoted by small d. So this is crushing area, also called as resisting area. Now I'll say that after this crushing area is area of a rectangle. So therefore, considering crushing of single eye end, therefore I'll write it on to the next page. Crushing strength of single eye end. Since we are writing strength means the load carrying capacity, load is denoted by P, and we want to calculate crushing strength. So therefore it is load is equal to crushing stress into area. So therefore area, it is D into T multiplied by sigma CR. So this is my equation number 4, and I can say that from this equation number 4 we can check the value of sigma CR. So from equation number 4, sigma CR, that is crushing stress, can be checked. So here we complete the designing of single eye end, that is, this was step number 2. Now as we have seen for single eye end, there were 3 kinds of failure: tensile failure, shear failure and crushing failure. Same 3 kinds of failure will be there for double eye end as well. So now in step 3 we will design the double eye end. In step number 3 we have design of double eye end. Now for double eye end also, the first kind of failure which we will consider, it is considering tensile failure of double eye end. Now how it will fail in tension, if I can explain it with a diagram, double eye end is in this way. It will look like this if I draw the 3D diagram for it. Now here this double eye end also carries a rod and it is hollow in section. So this is the double eye end, also called as the fork end. Now when we are checking for tensile failure, it will break into 2 halves from its center like this. If I can explain that with the help of the original diagram, here I have, when we are pulling this double eye end towards left, there are chances that it can break into half from this center line, break into 2 pieces like it was there for single eye end. So the shearing area will be here the tensile area, I can draw it, this, it will break into 2 halves like this. The area will look like. This upper eye will break like this into 2 halves, and similar kind of failure we will see at the bottom end also. So there are 2 failing areas. I'll draw that area. One area will be at the top, other will be at the bottom. It will look like this, because here I have drawn this eye end, it will break into 2 halves. This is the area at the top, similarly one area will be there at the bottom, so we are getting 2 pairs of area. This is the center of the double eye end or fork end. Now the thickness of the fork end, this is T1, and this diameter is same as the diameter of single eye end, that is, this is equal to D1, and this is the diameter of knuckle pin, D. So I am getting 2 rectangles here. Okay, it is here and the other rectangle here. So I'll say that there is 2 pair of area. So since resisting area capital A, it will be equal to, it is D1 minus small d into T1 Now I'm multiplying by 2 because here I have two such areas. So this is the resisting area. Now I can say that therefore tensile strength of double I end, that will be equal to P is equal to, since we want tensile strength, it will be tensile stress into area. So therefore tensile strength P is equal to area, which I have written here. I'll write this again, D1 minus D into T1 multiplied by 2 into tensile stress. Now this becomes my equation number 5. Previously 4 equations are over. Now I'll say that therefore from equation number 5 we can check the value of tensile stress. So sigma T can be checked. So this was the first step in the design of double iron, considering tensile failure. Now we will consider shear failure. Step number 3, design of double I end considering shear failure. Now when it is shearing, the example is like this. Since we have the fork end here, when we are applying a load here, there are chances of these two rectangles to shear, and how it will look like, it will be removed from this surface. That is, they will be shearing like this. Here I am drawing the shearing area. I am explaining how when it shears it will look like. So this is the shearing area. The plates, they would be moving away. That is, when we are pulling the fork end, these plates, they would come out from the top end, from the bottom end. So the shearing area is like a rectangle. These are two rectangles. Now if I consider this blue line as the center of the knuckle joint, or we can say knuckle pin, which I have denoted in the diagram. Here this is this center line. I will measure the distances from the center. So from the center of knuckle pin till the outer radius, this is the outer radius of double I end, which is equal to the outer radius of single I end. So here I'll mark the dimensions. This is the outer radius, which is R1, that is equal to D1 by 2. Next, this is the inner radius, which is R is equal to D by 2. So I am getting the area in such a way that at the top also it is double shear, and even at the bottom we are having double shear. So now the resisting area will be, therefore resisting area A, it will be equal to, this is outer radius minus inner radius, that is D1 by 2 minus D by 2 into, this is the thickness of double I end, that is T1, and here also this thickness is T1. So this D1 minus D1 by 2 minus D by 2 into thickness. Now I'll multiply by 2 for the first upper fork and again multiply by 2 because at both the cases we have double shear. So this 2 will get common and will get cancelled out. So the final area is 2 into D1 minus D into T. One of the two will get cancelled out. So this is the resisting area. So I'll say that after this, therefore shearing strength of double I end, it will be equal to, strength is the load carrying capacity as we know, shearing, therefore it is shear stress into area. So this is the strength equation. So finally I can say that P is equal to area, we have got 2 into D1 minus D into T multiplied by shear stress. So this is equation number 6, and I can say that from equation number 6, tau, that is shear stress, can be calculated. So after we have seen shearing failure of double iron, next we will see crushing failure of double iron. So again, in step number 3, we have the design of double I end, that is considering crushing failure. I'll draw the diagram for that. When it will crush, it will look something like this. At the top, at the bottom, I have two crushing area, and it would be crushed in such a way that is these dots which I am showing, these are actually fine powders of metal which would be formed when the double iron gets crushed. So here are the fine powders of metal which would be formed, and when these fine powders are formed, it means the double iron would be failing. So here is the thickness, which is T1 for top and bottom fork. Next, here after getting this T1, next D is the diameter. As we can see, for this double iron, when it is crushing, it is in contact with the knuckle pin. So here I have diameter of knuckle pin, that is equal to small d. So this D into T1, which is here the thickness, this is the crushing area because it is in contact with this knuckle pin, so it will crush, form fine powders here. So after this, I'll say that this is the diameter of knuckle pin. So therefore these are the failing area, or I can say crushing area. So these crushing area, they are A is equal to D into T1, and like this I have one more area, so multiply it by 2. So this is the crushing area. Therefore crushing strength of double I end, that will be equal to, since strength is load is equal to, here we are taking crushing into consideration, so load is equal to crushing stress, which is sigma CR into area, that is the resisting area. So now therefore I'll say that P is equal to area 2 into d into T1 into crushing stress. So this is equation number 8, and I can say that therefore from equation number 8 sigma CR, that is crushing stress, can be checked. So this completes our step number 3, that is design of double ironed is over. Now the last component which is left, it is the knuckle pin. So I'll say that next is step number 4, design of knuckle pin. Knuckle pin, it will be failing under shear. So considering shearing failure of knuckle pin. Now here I'll draw the diagram how the pin fails very quickly. Now knuckle pin would be shearing in this form, that is it will be breaking into 3 parts. As we can see, one portion, the middle portion of the knuckle pin is with the single eye end. So this portion will shear with single eye end, and the top and bottom portion are with double eye end. So they will go towards left and it will be shearing it this way. So the shearing area is a circle. Here I can draw the cross section area which is shearing. D is the diameter for this knuckle pin. So therefore resisting area A is equal to pi by 4 d square. Since it is a case of double shear, because we have one shearing area here, one is at the bottom, so this is a case of double shear. So here I have to multiply it by 2, and finally I can say that therefore shearing strength of knuckle pin, that will be equal to load P is equal to stress, since we are considering shearing. So we have shear stress into area. So therefore P is equal to, area is here, this is 2 into pi by 4 d square multiplied by tau, which is the shear stress, and this gives me equation number 9. So here I can say that therefore from equation number 9, either D, that is the diameter of knuckle pin, or tau can be calculated. So with this we complete the 4 steps, and in this video we have seen the designing of knuckle joint into 4 easy steps, that is starting with the design of rod, design of single iron, design of double iron, and finally the design of knuckle pin. And I hope whatever the explanation was there, that is understood in a simplified manner.